We don't have it? Okay. I'll give you an update.
I don't think I did this.
We can work through it. Okay, so let's see. Ice sculpture melts in such a way that it can be modeled as a cone, maintains a conical shape. So this R prime tells us how much the radius of the sculpture is decreasing. So by day 0 is decreasing by 6.1 inches per day. That's what that negative tells us. Day 3 is decreasing at 5 centimeters per day. So it keeps decreasing because it keeps melting. So here it says approximate R double prime of 8.5. So it's basically asking for the rate of change. What's the rate of change of the decrease? So we can just use slope, right? So slope, we want to find the rate of change on the 8.5th day, and the best we can do is choose the closest to 8.5, which is 7 and 10. So we just do slope. We just do change in R prime divided by the change in time. So yeah, so there's our rate of change there. And then our units will change as well because we started off with centimeters per day. Now we're dividing by time again. So centimeters per day or centimeters per day squared. Part B, is there a time in which R prime is equal to -6? Now, this is an easier problem because this is R prime in front of us, and we can tell that, well, we have a continuous function. The only way we're going to get from -6.1 to -5 is if it crosses -6, right? So this is IVT. So intermediate value theorem says if my function is continuous and if I start off with a value below my target, and if I end up with a value above my target, I got to reach my target somewhere.
On the example, I have to say all that.
Yeah, you're gonna have to. Yes, but I think IVT can be a little it can be a little awkward in terms of like the phrasing of it, and something that can be a little bit wordy. It's like, how do you say all those things? Like, it's easy to understand, but it's hard to get it out in words. So I think this is the most efficient way of doing it. You can do it other ways, but the grader wants to see that you're picking two values to prove that there's a value below and above. And then I'm also indicating where those are coming from. Those are coming from the endpoint. So I think this is the most efficient way of getting that information out, but this is not the only way. No. Question. Oh, and then this is non-calculator section. So you will probably just want to leave your answer in this form, right? You don't want to be subtracting it, but you do want to.
Can leave it that.
Yeah, you can leave it in this form, but you got to go further than this. You got to get these down to a number. Yeah. But once you're here, you can just say here this centimeters per day squared. You don't have to get down to 0.2. Part C, use right Riemann sums. We're working through number 4 on page 4.
Right.
Right Riemann sums. So how do you feel about right Riemann sums here? Like identifying the width and the height and adding up rectangles.
Like if I was good on it, but I'm
okay. So So the way you find the width is you subtract each of the subintervals. So 3 minus 0 is a width of 3. 7 minus 3 is a width of 4. 10 minus 7, and then 12 minus 2. Okay. So the numbers up here is the width, and then the height is going to be from the bottom row.
Yeah.
And then for each subinterval, there's either a left or a right. You want to use the right one. So the first rectangle will be 3 times -5. And the second one will be 4 times -4.4. And then so on and so forth. Again, non-calculator. So you probably just want to leave your answer in this form. You're not going to be able to get down to -51, but it's okay. Your units of measure is going to be centimeters though, because I think the tendency is students, they see the centimeters per day and they want to keep that unit. But whenever you take the integral, you're going to strip away the unit because you're multiplying these together. So if I do centimeters per day times day, then the days will cancel out. It's just centimeters. So yeah, keep in mind, whenever you do integral, your units will change and it'll be without the denominator, basically. Okay, good. A through C.
Yeah.
Part D, the height of a cone decreases at a rate of 2 centimeters per day. So that's, and you see that per day here. The radius is 100 centimeters and the height is 50 centimeters. Find the rate of change of the volume of the cone. So we see with respect to time. So whenever you see respect to time, that should give you a kind of a hint that there's the related rates going on. So with the related rates, we were always starting off with an equation, and then we're finding the derivative, and then we're attaching all these d over dt's for each variable. So we're given our cone formula, which is 1/3 pi r squared h. And we have to find the derivative. So notice that there are two variables at play. You got the r and you got the h. So we have to go through product rule. Okay. So to go through product rule, we got to do f prime g plus f g prime. So the derivative of 1/3 pi r squared will be 2/3 pi r times dr dt. And then the h will stay the same. And then back to f, 1/3 pi r squared. And then h's derivative is 1 times dh dt. So when you find your derivative with related rates, every variable, in this case, the v, the r, and h, will all have its turn with the d over dt for that variable showing up. All right. Okay, so are you good with dvdt here? Okay, so we're going to find all the values to plug in. So radius is 100 centimeters. That's given in the problem. H is 50 centimeters. dr dt. it doesn't give it to us in part D, but we do have R prime, and R prime is dRdt. So we know that on the third day, my dRdt is -5. So just have to be able to make that connection that R prime is dRdt, and then replace that dRdt with -5. And then dHdt, the height is decreasing by 2, so we want that to be a -2. And then you leave your answer unsimplified. We don't want to spend the time to clean this up without a calculator. So, and then our units of measure, cubic centimeters per day.
Non-calculators no need to.
Yeah, exactly. Yeah, not a calculator.
You ever draw out the situations going on for related rate problems?
Not unless it's like a Pythagorean theorem problem, and I want to know like, oh, you know, plane is traveling in this direction, and I just want to know, you know, whether to make a rate positive or negative because something's getting smaller or larger. So I usually don't draw anything out unless it's like Pythagorean theorem. No. Other than that, I know I got to get to my derivative and it's just have to plug everything in. There's no need to. I don't think there's a need to draw it out unless it's like a triangle. Okay, good with 4. All right, so here's number 5. Page 5. Consider differential equation dy dx. A portion of the slope field is given. Sketch the solution curve. So it's as easy as just finding that order pair and then just following the flow of the graph throughout. Okay, part B, write an equation for the line tangent. So what information do we need if we want to build our tangent line equation? Point and slope, right? So the point is given to us, which is 1, 2. To find the slope comes from the derivative. So your dy dx is your derivative. So we can just plug in that order pair into that derivative and get a slope value. Okay. Again, without a calculator, so we do need to recognize our unit circle values. Sine to the power 2 is 1. Root 9 is 3. 1/2 times 3 it's going to be 3/2. So that's our slope. Okay. So once we have our equation of the tangent line, well, we can do y minus y1 equals m times x minus x1. Get y by itself because we still need to do linear approximation. So the last step is replacing that x with the value that they asked you to approximate. So it says approximate f of 0.8. So we got to plug 0.8 in for x. Again, without a calculator, so you're going to just get it down to unsimplified version. Okay, part C. Since f double prime is greater than 0, so what does that mean? What does that mean for the shape of the graph? Concave up, yeah. So is the approximation over or under approximation? So if my graph is concave up, how is my linear approximation going to look? Will it be under the curve or above the curve? Under, yeah. So concave up is going to have this shape. So my line is going to be, no matter where I draw the line, is if it's a tangent line, it's got to sit below the curve. Okay, good. A through C. All right, so here's part D. Yeah, part D is going to be the one that takes the longest time here. Use separation of variables to solve the differential equation. So we're going to have to get our x's together, our y's together. So first thing, I'm just going to cross multiply. I'm just going to go ahead and move that dx over to the right side here. So right, I want to get my dy and dx's lined up on opposite sides. These are my anchor variables here. I know I want these in place. So now I'm going to decide, do I have full separation of variables still? Are my y's all together? Are my x's all together? Well, I think something is out of place. What needs to move?
Why?
Yeah, see that this y plus 7,
Yeah.
right? So how can we move it? What does it look like if we move it? Well, we have to move it, right? So we don't want to do any calculus just yet, just in terms of moving it. How would you move it?
Square that.
What I mean by moving it is, how can I get this to the left side of the equation?
Separate it from that plus 7.
And how what operation would you do? Would you add, subtract, divide, multiply? Divide. Yeah. So we're going to divide this over to this side, right? Because all these are being multiplied. Now, if it was being added, then I would subtract it, but these are being multiplied. So the way you undo multiplication is division. So if we divide that root y plus 7, where's it going to end up?
On the left.
But where on the left side? Numerator or denominator?
The
Denominator, yeah. So dy divided by root y plus 7 is equal to 1/2. Now, we haven't done any calculus yet, but just by going from here to here, you've earned 1 point. So are we comfortable being able to get our variables separated here?
So you bring it plus 7 too, right? And so
We have to, right? Because this y is all contained within that square root. So anything that's attached to it, we got to move it. Yeah. Inside the square root, if it's inside the parentheses, yeah, we don't want to separate that. Okay, good so far. Okay, now the left side here, how can we, now that we have full separation, we can go into our integral step. And what do you think we have to do here to get it ready for our integral? And can you identify the integral rule that we're going to use on the left side? Maybe I can get a set of parentheses to show up. Would that help? Chain rules for derivatives.
Oh,
Eventually, yes, but something we should handle first, because this is a little bit, yeah, use substitution, right? Use substitution will eventually get us to the point where we can at least go through, yeah, we can discover what rule we want to do on the left side. The right side is also use substitution because we got to clean this up, right? We're trying to get this to be a cleaner or a more recognizable integral rule. Okay, so what could be our u value on the left side? Because these are two separate problems. We'll do them one at a time because they're going to be each its own step. So you say substitution, that's good. What could be our u value on the left side?
oh, yeah.
Y plus 7, yeah. So if you're ever questioning what the u value is, always start with what's inside the parentheses. That's usually going to be where your u value is going to be. Okay, what's the next step with u substitution?
Du.
Du, dy. What's derivative? It's 1. Okay, cross multiply. Make your substitution. Okay, this is cleaned up, right? It's an easier version of what we started with. The whole purpose is so that we can get this to be more recognizable. What rule do we use with this? Yeah, how can we tell if it is natural log or not natural log?
So many exponents.
So you want to
If it's 1,
Yeah, if it's 1, then we use what?
natural.
Natural log. But if it's not 1, we use what rule do we use? It's just use the 1/2. Power rule.
It's sorry.
Yeah. But can I leave this in the denominator if I want to do power rule? Okay, where does that have to be?
Numerator.
Okay, so how would you get it to the numerator?
Use -1.
Yeah. Okay. All right. Do you remember power rule for integrals?
We use it 1/2 divided by.
Yeah, we add 1 to the exponent, right? Divided by the exponent. Good. Okay, so u to the 1/2 over 1/2. And that cleans up to be what? Dividing by 1/2 is same thing as. So 2u to the 1/2, and then we can bring back our original variable, right? We're done with the calculus, and now we can bring back the variable y. Okay, so we can come back to that once we get that right side to the same level as this, but the right side still requires u substitution. So what's our u value on the right side?
Yes.
Okay, derivative. Cross multiply. Solve for dx. Make your substitution. Okay, what does this clean up to be? Anything cancel out here? Twos, okay, and then I can push out a what in front? Yeah, that 1 over pi is just a number, right? So it's just a coefficient out in front. Okay. And then, do you guys remember what's the integral of sine? Negative cosine, yeah. So negative 1 over pi cosine of u plus c. And then we can bring back our original variable, which is pi over 2x. All right, final stretch here. We have these two that we can finally set equal to each other. And then we have 2 more things left to do. We got to solve for c and we got to solve for y. So at the top here. I'm going to go ahead and just solve for c first. Just get that out of the way, and then I can solve for y by then dividing 2 and multiplying by raising both sides, squaring both sides. So to solve for c, I'm going to take my order pair 1, 2. So plug in 1 in for x, or x, replace x with 1 and replace y with 2. Okay. 2 plus 7 is 9. Square root of 9 is 3. Cosine of pi over 2 is 0. And so c is equal to 6. So now that I have my c value, I'm going to update my equation, and then the final thing is to solve for y. Okay, so 2 more things left to do. To get y by itself, I'll divide everything by 2, which is the same thing as multiplying by 1/2. And that can square both sides. And that can move to 7, and then that y can be by itself. Okay, square both sides. And finally, we'll move that 7 over to the right. And then there we have it. It's a long problem, right?
Like point for each step you do for each case.
I'm sorry.
What's the point distribution on that?
Oh, This is probably like a 5-point problem. You got 1 point for separating the variables, 2 points to be able to do the calculus correctly, use substitution, get it up to this point, and then 1 more point to solve for C, and then 1 more point to solve for Y. Okay. We'll talk